So what we'll do is, for this last example in Chapter 7, we're going to look at an example where we need to invoke resonance. So for this, it asks us to draw the resonance structure of nitrous oxide, which is used as an anesthetic and also in whipped cream as a propellant. And this consists of 2 nitrogen atoms and 1 oxygen atom per molecule. So it asks us to show the resonance forms and to calculate all the formal charges in each of the resonance forms. Now, before you get started on this, I will help you out a little bit. So it's going to be helpful to know that sort of the skeleton of this molecule is going to have a nitrogen, and then the oxygen, like this. So 1 nitrogen is our central atom, and the other nitrogen and the oxygen are going to be the outside atoms. And another thing to kind of help you out here is the total number of resonance forms that you get for this should be 3 different resonance forms. So with that knowledge in hand, go ahead and pause the video, and I'll come back in a couple of seconds and start walking you through this. Okay, so hopefully you've tried this problem on your own. With any example, we need to know how many valence electrons we're dealing with. So each nitrogen has 5 valence electrons, and there are 2 of those, so 2 times 5. And then we need to add to that 6 electrons from our 1 oxygen. So 2 times 5 is 10, and 10 plus 6 is going to be 16 electrons. And I kind of already did step 2 for you. I showed you what the skeletal structure should be here. Notice that we have 2 bonds in this structure. So we used up 4 of our 16 electrons, meaning we have 12 remaining after we put the skeleton together. So the next step is going to be to assign these remaining electrons to outside atoms first to complete their octets. And the nitrogen on the left and the oxygen on the right both only have 2 electrons around them each right now. So we need to give them 6 more, so 3 lone pairs. And if we do that for 2 atoms, we'll exactly use up our remaining 12 electrons, so that's good. We won't have to assign any to the central atom. So we have a lone pair, 2 lone pairs, 3 lone pairs around the left nitrogen, and 3 lone pairs around our central oxygen. So this is what we have after step 3, and indeed after step 4 as well. Since there's no electrons left, we can't put any on our central nitrogen. Now we come to step 5, and this is where resonance shows up for pretty much any resonance example. Now, if we look at our central nitrogen right now, it's in a pretty bad state. It only has 2 pairs of electrons around it, 2 bonding pairs of electrons, one with another nitrogen and one with an oxygen. Now, that means it has 4 electrons, so to give it 8 electrons, we need to basically get 2 of those lone pairs that are on our outside atoms and come up with some resonance forms that use 2 of those lone pairs to fill out the octet of our nitrogen. And I said you have 3 choices here for 3 different resonance forms, and those 3 choices are: we could take both of those lone pairs from the nitrogen on the left-hand side, so that would leave us with 3 lone pairs minus 2 lone pairs, so just 1 lone pair, and both of those are bonds now, so we go from a single bond to a triple bond. And our oxygen is the same. Another option would be to take 1 lone pair from the nitrogen and another from the oxygen. So each of the outside atoms will have a double bond to our central nitrogen and 2 lone pairs. So we took 1 lone pair from each. And our third option is going to be to take both of the lone pairs from oxygen. So it's kind of like the mirror image of the first example that we looked at. So we'd have a single bond still between our two nitrogens, 3 lone pairs around that middle atom, or I'm sorry, around the atom on the left, and then we took a single bond and 3 lone pairs and turned it into a triple bond and 1 lone pair for this oxygen. So these are all different resonance forms, so we should probably put some arrows pointing in both directions between them. So this shows that these are 3 different resonance forms, and these are the final 3 resonance forms for these. Now, if we want to compare how well each of these things represents the true structure of nitrous oxide, N2O, what we can do is we can look at the formal charges on each atom and kind of compare and contrast them, see where our negative and positive formal charges end up and whether they're kind of idealized. So I'll go through in detail the calculations of the formal charges in the structure on the left-hand side. So I'll do the formal charge calculations for the left nitrogen in green, the central nitrogen in orange, and oxygen, I'll do that in purple. And if you go back a few slides, the formal charge for our green nitrogen should be the number of valence electrons in a neutral nitrogen atom, which is 5 minus 1/2 times the number of bonding electrons, so not the number of bonding pairs, but the number of bonding electrons. This nitrogen has a triple bond right here, so that's 6 bonding electrons. And then we're going to subtract the number of non-bonding electrons. Again, not pairs, but actual total number of electrons, which is 1 lone pair, so 2. And if you do this with the correct order of operations, we end up with a formal charge of 0 on our leftmost nitrogen. And remember, a formal charge of 0 is kind of the best case scenario. So if you have a resonance form where all of the formal charges are 0, that's probably a good indication that that's a good resonance form. Now let's look at the nitrogen here in the middle, which I'll do in orange. So we need the number of valence electrons in a neutral nitrogen atom, 5. We're going to subtract 1/2 times the number of bonding electrons. Now this nitrogen in the middle has 4 bonding pairs around it, so that's 8 bonding electrons. And subtract the number of non-bonding electrons. We don't have any lone pairs, so that's just 0. If you follow order of operations correctly here, we get 5 minus 4, which is positive 1. I'm going to indicate that as explicitly positive because positive versus negative is important here. So that's going to be positive 1. And then for our oxygen here on the right, we can calculate its formal charge as the number of electrons, valence electrons I should say, in a neutral oxygen, which is 6. Subtract 1/2 times the number of bonding electrons, so 1/2 times, we have just a single bond here, so the total number of electrons there is 2, minus the number of non-bonding electrons. 3 lone pairs gives us 6 electrons there. And if you do all that in your calculator, you should end up with -1. Now, one way to check your formal charge calculations is that all the formal charges on all the atoms should add up to whatever the charge is on your molecule or ion. So in this case, nitrous oxide, N2O, there's no charge indicated on that, so all the formal charges should add up to 0. And indeed, we have 0 plus +1 plus -1 gives us 0. So that's a good indication that we did the formal charge calculations correctly. Now, things to notice here is we have some formal charges that aren't 0. So on the central nitrogen, we're +1. On the oxygen were -1. That is not as good as if we were to somehow have all 0 formal charges, which none of these structures will. But if we have a negative formal charge and a positive formal charge, then the -1 should end up on the more electronegative atom. And oxygen, being to the right of nitrogen, is going to be more electronegative. So if we have to have a negative formal charge, it's probably good that it's on oxygen instead of nitrogen. Now, since I went through those calculations in detail, I'll just show you for the other examples what the formal charges should be for all the atoms. So in both examples, you're going to end up with +1 on the central nitrogen, because it always has 4 bonds and no lone pairs. For the nitrogen on the left, for the central one, it's going to be -1, and for this one on the right, it's actually going to be -2. And it's worth pointing out that formal charges are less ideal if they're non-zero, and the further away you get from 0, the worse they are. So a formal charge like +2 or -2 are usually signs that the resonance form is not that good. And then finally we can go through and calculate these for the oxygen. So here in the middle, that's going to end up being 0. And here on the right, when we have 3 bonds and 1 lone pair, which is not the normal state for oxygen, that's going to end up being +1. Now in all these situations, if you add up the formal charges, you get 0. So -1 plus +1 plus 0 is 0. And then on the right, -2 plus +1 plus +1 is also 0. Now, if we look at our central resonance form, right here, we can see that we have a +1 on the central nitrogen, so nothing has changed from the one on the left in that respect. But we took our negative formal charge and essentially shifted it from oxygen to nitrogen. So we shifted it to a less electronegative atom. So that resonance form in the middle is probably not as good as the first resonance form that we drew on the left. And if we look at the resonance form here on the right, this not only has all non-zero formal charges, which is bad, but we also have a positive formal charge on the most electronegative atom and a -2 formal charge on a less electronegative atom. So there's all kinds of indications here that this is probably not the best resonance form in terms of representing this molecule. So this form on the right is the worst representation, and this form on the left, where our negative formal charge ended up on oxygen, is going to be the best, and the one in the middle here is going to be intermediate between the two. So the true structure of nitrous oxide is going to be some combination, or really I should say some average of these 3 resonance forms, but that average is weighted more towards this thing here on the left-hand side, and less towards what you see there on the right. So those are your 3 resonance forms and how you can rank them for nitrous oxide. And that brings us to the end of the examples that I wanted to cover for Chapter 7. So I'll go ahead and stop the video here, and I will see you next time when we start with Chapter 8.